Everyone's favorite sound, recording in progress. Okay, so let's just do a recap. Last week was a little while ago, and what we wanted to do was really take our one-dimensional steady-state diffusion equation, cast in our finite volume formulation, and apply it to a stencil or a grid. So what we had was the following. We were able to solve for our conserved quantity of interest at the center of our stencil, P, based upon the quantities to the left and right, i.e. phi west and phi east respectively. And we had our weighting coefficients, AP, A west, A east, where A west was defined as the area of the interface between our west and our P cell times our diffusivity at that interface per the distance between our P and west cell centers, delta XW. And then A east is once again the same. A underscore E, that was our interfacial area between our cell center P and our other cell labeled E, times the diffusivity at that interface per the spacing between cell center nodes. And AP was just the summation of A west and A east. So what we did is we looked at this really simple problem that we already knew the solution to. Because our thermal conductivity, i.e. our diffusivity constant, was constant at 1 watt per meter K, and we just applied 2 Dirichlet boundary conditions, and we didn't have any variable cross-sectional area. So we went through and we applied our stencil. We started on the interior of our system, where we started at node 2, and we indicated this to be, the center of our stencil. So AP T2 minus A east T3 minus A west T1, where T1, T2, and T3 correspond to our conserved quantities at our cell centers. In this equation, this left-hand side, we then set equal to 0. And we move through our stencil doing for our interior control volume, CV2, CV3, CV4. And then we applied our stencil at cell centered or our control volume 1, where APT1 minus A east T2 had to be minus A west T0. And we contrasted this to the finite difference method, where in the finite difference method, right, we created a ghost point out here, and we did a little bit of algebra and solved for the temperature at our boundary based upon what was happening on the inside. That was, for a given flux condition. Here we don't have a given flux condition. We're going to talk about that momentarily. But all we had to do is recognize that we could take this value at our boundary, T naught, and it'd have a leading coefficient, A west. Now, A west was equal to the interfacial area, which would be this area, times the diffusivity at that boundary per delta XW. Now, delta XW is just 1/2 of delta X, right down here. So AW was then multiplied by a factor of 2 in comparison to everywhere else. We did the same thing on our ending cell, CV5, where APT5 minus A east T6, this guy right here is T6, minus A west T4. Once again, when we calculated A east, the coefficient, for T6, our Dirichlet boundary condition on the right-hand side of our system, we recognize that, it was delta X per 2, and that 2 came up within the numerator. So what we were able to do is construct a system of equations. And what we had was APT1 minus A east T2 minus A west T naught is equal to 0. T naught was a boundary condition. So we were able to kick this over on the right-hand side of our equation. That was pretty nice. So in matrix form, we had AP T1 minus A east T2, and this would be equal to A west T naught. We went through and populated our diagonal and off diagonals. This is a tri-diagonal matrix, 3 diagonals. And when we got to our last CV5, we recognized that this guy was a constant. So we moved him over here. It was a positive value. Now, when you guys are coding this stuff up, I made this mistake today. it's really easy to drop your coefficients into your B matrix and forget to multiply by your temperature boundaries. So just be careful. I made that mistake today and spent an hour troubleshooting my code, line by line, checking everything by hand. Everything was perfect right up until I constructed that B matrix. So it's really easy to forget those temperatures. Now, I provide you guys just a rough code of how to do this, the calculations of the coefficients, the pre-calculations of, our arrays, just so things go a little quicker. And that was Total Lecture 2 Example 1.m. And you guys could have a chance to pull that down. Now we're going to look at that code and an extension of that code a little later this evening, once we get into our non-constant grid spacing. Now, before we do that, we have to talk generally about our boundary conditions. So in that previous problem, we had two Dirichlet boundary conditions. We had two temperatures. And I say that problem is trivial because the left-hand side was 100 degrees, right-hand side was 200 degrees. Everything was constant, so we'd expect a linear temperature profile. And that's great. But we know that there are other boundary conditions, like a Neumann boundary condition, i.e. we are providing a flux. So sometimes we'll have a problem that has two fluxes. Sometimes we'll have a mixed problem where we have a Dirichlet and a Neumann. And we want to make our code as robust and adaptable for that. So what we're going to do is we're going to tack on a new term, AB phi. And the B stands for boundary. Now this is really useful because if we look at this equation right here, this is the same that we've actually come up with for our 1D diffusion problem. Now just to jog your memory, right, that looks so simple. But what we did was we reduced this equation down into that really beautiful scalar formula, and that equation was the result of integrating over our control volume, i.e. actually an area, since this was a 1D diffusion problem, of our governing equation. This guy. So although it looks incredibly simple, don't forget that we put a lot of work into actually constructing this equation in a very kind of elegant and useful form. Now, what we want to talk about is this boundary. So AB phi, if this is our conserved quantity, phi, this is great for a Dirichlet boundary condition. And what we're going to do is if, say we're looking at control volume 1 from example 1, we would set A west phi west to 0 and then populate AB phi. If we were looking at control volume 5, we would set A east phi east to 0 and then populate those of our boundary. It's just a way for us to note that when we are on a boundary and we don't have a cell exterior to our domain, that this calls into attention that we should be treating our coefficient differently than we've treated A west and A east. Now, most texts don't do this. I like to do this because it's just a really good way to check yourself that you're actually taking that delta x divided by 2 correctly into account. Now, that's a great way to modify our equation for a Dirichlet boundary condition. Now, if we have a flux, we're going to simply tack on Q. So we've expanded our equation to simultaneously include Dirichlet-Neumann boundary conditions. If we don't have a Dirichlet boundary condition, but we're supplying a flux, we can set that equal to 0. And then it depends upon, what end of the bar or domain we're looking at, that we can set our remaining values equal to 0. Now, if we don't have a flux, we can just set Q equal to 0. This way is just, really calling to attention that we have to treat our boundary conditions separately than we treat the interior of our domain. You don't have to adapt this convention if you don't like it, and you can just run with our original equation as here. Nothing wrong with that. But without really paying attention to A west and A east on those ends, really simple mistakes can happen that take a while to troubleshoot. Now, what we can define is simply AB, our coefficient on our boundary would be the cross-sectional area of your boundary times 2 times the diffusivity of our boundary per delta x, where we note the factor of 2 for our delta x was divided by 2 in our denominator. So that really remains unchanged. Now, as I mentioned, we have our two types of boundary conditions. Dirichlet, where we have a constant conserved quantity, i.e. a constant temperature. And Neumann is new, but Neumann you see quite a bit when you're prescribing a heat flux and you're waiting for that temperature to evolve, because you can't simultaneously provide a flux and a temperature, because you'd have two boundary conditions in one location for a second order differential equation that need at least one boundary condition on each end. So what we'd specify is for a flux, we're going to indicate that we'd have a positive diffusivity times the gradient of our conserved quantity phi, evaluated at the boundary. I guess I should make that a lowercase, huh? Just for consistency. So for you guys who like heat and mass transfer, you've probably seen this before, right? If you have a flux Q double prime, you'd have minus lambda grad T, because your flux is going to go from a high potential to a low potential, where you have your diffusivity, i.e. your thermal conductivity, times the gradient of your conserved quantity. Now here we're just going to note that this is a positive quantity. And what we'll say is JB, where J was the variable we used to specify a flux, is evaluated at our boundary. And regardless if we have a flux or we have a constant temperature, both of these move to the right-hand side of our equation. That is, as we come back here, right, this would be AB phi B. Our coefficient at our boundary times the conserved quantity at our boundary, if that was a constant temperature. And if this was a flux, all we have to do is move JB right on over. So that's really easy to incorporate these boundary conditions. Incredibly easy. And you're going to see that on a homework assignment. Now, to summarize, we can cast our governing equation for 1D steady state diffusion as follows. I just did a little bit of a rearrangement. We have minus A west phi west plus AP phi P minus A east phi east. I did this rearrangement because this is typically how you see it on the diagonals of your matrix. The A west coefficient, or the negative thereof, is the first off diagonal, your lower diagonal. Then you have AP leading phi P, which is the diagonal of your coefficient matrix, minus A east, which is a coefficient to phi east, the negative thereof, which is now the upper diagonal. And this would be equal to your Dirichlet boundary condition, AB phi B, and it would then be plus a Neumann condition if you have that. Now note, you can't simultaneously have a Dirichlet and a Neumann. Things get weird, so it's either or, right? If it's Neumann, you set this guy to 0, or if it's Dirichlet, you set this guy equal to 0. Once again, we have our coefficients defined as such. So this is the most generalized form of our code. It's the most generalized form of our system of equations. And it's really easy to use. You guys are going to see that later on when you guys are then going to do your first homework assignment considering a flux.
I have a question.
Yeah.
So like why can't we have both a Dirichlet and a Neumann? Can't you have a problem where you have a fixed temperature on one end and then a flux on the other?
Well, we can. That's a great question, Josh. So we can specify a temperature here, and we can specify a flux here. And that makes perfect physical sense. When we're specifying this equation, I should mention that it's only at one control volume. That is to say, our problem would be ill-posed if we specified both the flux and a temperature here, because that would provide two boundary conditions for our second order differential equation. And then if we specified anything on this end, it'd now be an overspecified problem. We'd have basically three boundary conditions where only two are necessary. So we can't apply both a Dirichlet and a Neumann in the same stencil. Say this is control volume 1. Here is our east, here's our P. We can't specify both temperature and flux on this western face.
Makes sense. Thank you.
No problem. Yeah, thanks for bringing that up. I wasn't too clear that first go around. So yeah, you can definitely provide a flux here. See how your temperature evolves, and then you can put a constant temperature boundary condition down here. Or if you want, you can have two fluxes. Or you can put a temperature up here. And you can mix and match. You can just have as much fun as you want.
If you had two fluxes, would you need to specify your initial conditions?
Yeah. So two fluxes. What you'd have to be incredibly careful of is you're really upholding the conservation of energy. For definitely a steady state solver, energy has to be conserved. So if we think about this as a bar of copper and it was perfectly insulated and there are no source terms, your flux in has to be equal to your flux out. So yeah, you can definitely provide decent initialization for the temperatures throughout your domain. And depending upon your initialization, if you are too far out, your system of equations might not converge. It might just diverge into a nonsensical solution. So kind of like two Neumann boundary conditions is always a little bit difficult because you'd have to consider, first of all, you're conserving energy. Now, say you have a source term within your system. Sometimes you can make a system of equations where it won't converge, or it will converge to a different set of solutions, depending upon how you perturb it. But a double flux situation they exist. So our lab, we do waste heat recovery of exhaust gases. So you're actually providing a flux to the hot side of a heat exchange system with thermoelectric generators. And on the cold side, you basically have a convective boundary condition. We're also specifying a flux. So your top side's really defined by H and a free stream, and your cold side is defined by H and a free stream. And these two temperatures at the bounds of the system and all temperatures throughout evolve as a function of those supplied fluxes. But if your initialization is off, sometimes it won't converge, your solution will blow up. So you always have to start in an incredibly kind of low flux state and keep using those initializations as you move up to, say, higher temperatures and higher fluxes. So it is possible, yeah, you just have to be very careful about your initialization. And just have to accept the fact that, hey, the code might blow up. That's common. There's nothing better than MATLAB just spitting out NANs. First iteration goes right to NAN. It's like, okay, this is how today's going to go. But we'll, depending how much you guys like this coding, we could definitely work through a whole bunch of these. So these are really the boundary conditions we're going to work with. And you're going to see your Neumann boundary conditions on your first homework. You're also going to see non-constant cross-sectional area. And don't worry, because today we're going to talk about how to handle some of that via an example of a non-uniform grid. Now, the last thing we have to talk about is our interfacial diffusivity. Now recall when we apply our stencil to our west, our center, and our east cell, that we're taking our diffusivity, we do a gamma west, and we have a gamma east, right? And we're assuming that is a known diffusivity at the interface of our control volumes. Now, more often than not, your diffusivity is a non-constant value. It's going to be a function of temperature. So that's always fun because you first would have to know the temperature of these filled centers, and then we can do linear interpolation, everyone's favorite. Now, I know Joe and Marissa, and I don't know if Ben took thermo with me.
Oh yeah, I had thermo.
I didn't.
So a good number of you guys had thermo with me as well as fluids. And I said, this is really important. Interpolation is going to come back one day to haunt you. Same with RTT. And here it is. Because the main method to determine an interfacial diffusivity is straight up linear interpolation via the lever rule. So if you know the temperature in your west cell, the temperature in your centered cell, you can evaluate your two thermal conductivities and linearly interpolate to determine your interfacial diffusivity. That is, we can say our interfacial diffusivity is going to be delta, the distance that we move from P to east. And recall that this guy, the total distance between P to east, our cell centers, was delta XE. So delta times the diffusivity in the eastern face plus 1 minus delta times the diffusivity in the centered face. Or sorry, not face, cell. So we could just arithmetically average these. And right now I made that interface just a little bit funny, just so we could see how this looks. Now, delta is just going to be our location, x, at where this interface is existing between our two control volumes. So this location right here is x minus xp over xe minus xp. So if we look at this arithmetic average, if our interface is at xp, delta goes to 0, and we are just going to take the diffusivity of our P control volume, our center control volume. And as x tends to xe, i.e. delta tends to delta xe, delta is going to be equal to unity, and our diffusivity is going to be taken at our east cell center value. And at the midpoint, it's just, our mean, our average. Now, linear interpolation works well for single material domains with no insulated or adiabatic boundary conditions. And we could easily use a linear interpolation scheme on the interior of our domain to determine our interfacial diffusivities. All right, so everyone's pretty familiar with interpolation. This is nothing more than what you see in your undergraduate thermodynamics course. I'll take the silence as a yes. Cool. So, we just interpolate and we can determine our diffusivity really any point along our system. But oftentimes we just want to evaluate it at gamma west and gamma east, because those populate our coefficients A west and A east. Now, linear interpolation, although it's great for the interior of the domain, has some catastrophic flaws. Imagine this. Imagine we have our cell center P, our control volume P, and our control volume E. Now, let's say we have two different materials. Let's call P copper, and let's call E asbestos, because it's horrible, and it's a really good insulator. We could call it glass or what have it. Now, let's assume that this insulator, let's not use asbestos because we all don't want lung cancer. Let's, pick a really good insulator where we can assume our diffusivity is equal to 0. Now, if we used our interpolation scheme and we wanted to determine the diffusivity, gamma east, which is equal to our diffusivity, lambda east at the interface, which we'll just call lambda int, since it's midway between cell center P and cell center E of our two control volumes, we would get an interfacial diffusivity of 0.5 lambda P. So say this was equal to 1, and this was equal to 0. If we do our arithmetic mean, i.e. our linear interpolation, 1 plus 0 divided by 2 is 1/2. Okay, so this is bad because if we have a perfect insulator, what we're saying is if this is perfectly insulated, our flux J, and you can think about this as a heat flux, Q double prime, this would be equal to 0, right? Because Q double prime is equal to minus lambda grad T. Now, in this particular situation, these two temperatures would differ. And now that lambda is a non-zero quantity, we have a flux. And we go, if this is a perfect insulator, heat can't enter it. Because if heat enters it, our temperature is going to increase. And by definition of a perfect insulator means we can't have heat entering. So we go, okay, linear interpolation has failed us. Well, what can we do? Now, we can try something a little bit different.
Cry.
Did you say cry, Andrew? Alex?
Maybe.
Yeah, as if you've ever taken any classes with Professor Givey, he just says pray, and you hope something works out. Now, what we're gonna do is get a little bit clever. And we're gonna do something called harmonic averaging. Now, let's just go back to our definition of a flux, right? J would be equal in one dimension, right? Because recall Q double prime is equal to minus lambda grad T. So in 1D, we can say J is equal to minus lambda at our interface, because this is where our coefficients are being evaluated, dt dx. Now, dt dx, if we do a backward difference scheme, this would be T in our right cell, so our conserved quantity in the cell center, which is T of E, minus T of P per our distance, and that's delta XE. Okay, so what we can then do is we're going to do a little substitution down here. Now, we want this guy, lambda, to be expressed in such a manner that if we do have a perfect insulator, we have no heat. But we don't want to develop in our code just, a logical check that says if this equals 0, set this to 0. Well, that's something a little more robust. So what we're going to do is leave our numerator TE minus TP, and then in our bottom, we are basically going to, I'd say, in a manner, apply lever rule. Now, recall lambda int previously. We just kind of did an arithmetic average. Or what we're able to do is, in this manner, define delta as really how far we are going from our cell center at P to our cell center at E, and use the lever rule, right? Where we had delta gamma E plus 1 minus delta gamma P. Now, in a manner, we're going to do something similar, but we're going to define an effective diffusivity. And what we're going to do is really define lambda as 1 minus delta per lambda P plus delta per, and I should fix that, lambda E to the inverse, i.e. this would populate the denominator of our flux expression. Now, in this harmonic average, this makes a little bit of sense. Now let's look at this for a moment. If delta is equal to 0, i.e. we are right here, this term cancels out, so we just have lambda P up top, and this term goes to 0. So we still have a flux through that material. But as delta goes to unity within the system, this guy drops out, 0, and we'd have 1 divided by our diffusivity of our E material. Now, the only issue is, right, we have to be a little bit conservative about lambda E, because we divide out by 0, which is going to throw a NaN. So there's going to have to be some check in here to set a value. Now let's look at this in just a practical application. Say we were looking at two materials, P and E. We wouldn't go all the way for delta is equal to unity, right? Because we're trying to evaluate this at the interface. Oftentimes for a uniform grid, delta would be equal to a half, because we're trying to solve for interfacial diffusivity. So if we do this, we'd have 1 minus 0.5 per lambda P, which is just 0.5 per lambda P, plus 0.5 per lambda E. And this is to the inverse. Or this gives us 2 lambda P lambda E per lambda P plus lambda E. Now, in this manner, if we actually execute this inverse here, we have a much nicer expression. In such a way that at our interface, we'd have 2 lambda P lambda E. If lambda E was equal to 0, that we have a perfect insulator, this drops out. And we don't have a divide by 0 error. Vice versa, if lambda P is our insulator, this goes to 0. Once again, we don't have a divide by 0 error. That is, if either of these materials is an insulator, our flux will be satisfied as a 0 value. And this allows now for a large range of varying diffusivities within our system. So what we'll do is really use this harmonic average. And we'll obviously evaluate the inverse before we plug in any values of delta, because we don't want this, divide by 0 error within. So the harmonic average is a much better way for us to define really interfacial diffusivities. Now what's cool is, let's go back to this guy. Let's set lambda P is equal to, 10. Lambda E is equal to 6. If we did a straight arithmetic average, and delta was taken as 1/2 our distance, we would have a value of 8. Now in our harmonic average, what we're going to have is 2 times 10 times 6 plus 10 plus 6. So 20 times 6 is 120. Anyone tell me what this value is? My mental math isn't the strongest. It's 7.5. Now we go, okay, the harmonic average is really, really great, for a situation where we have an insulator. And we want a zero flux condition. But if we use it throughout our domain, it's going to give us a value different than arithmetic averaging, i.e. linear interpolation. That is to say, our harmonic average is always going to yield a lesser value than determined by our arithmetic average. And there's another way to look at this. Let's consider the situation where lambda p goes to infinity. We have a perfect conductor. What we can do is re-express our interfacial diffusivity when our distance in between our two cell centers was taken as a half. We can factor out down here, we can basically say, factor out a lambda p, and we'd have lambda p times the quantity 1 plus lambda e per lambda p. In this situation where lambda p tends to infinity, what's going to happen is this term will tend to 0, so we'll be left with 2 over lambda e per 1. Now this also places a limit on our system, which is good. So the harmonic averaging, in addition to being well for really good insulators, also doesn't allow too much heat to quickly flow through your system all at once. That is to say, in this situation of where you put in a super high thermal conductivity material, your interfacial diffusivity is actually going to be 2 times that of the lesser material. It's kind of going to be like rate limited. And within the harmonic average, this diffusion, the rate of it is going to be limited by your lesser thermal conductivity material. And that's just taking, the limit of lambda p tending to infinity. So the harmonic average has pros and cons. And we have to be very useful when we do this type of averaging. And really, the logic you have to put into your system is not setting, say, j is equal to 0 at certain instances. It's which averaging technique do we want to use when. So for a situation, of a specified non-zero flux, the arithmetic average is great. But if you do have an insulator, we have to use our harmonic averaging. And then what we're going to recognize is within our harmonic averaging, we're going to have an underprediction of that diffusivity. Is it going to be much? Well, in that previous example, we saw, using a harmonic average, we got a value of 7.5. Whereas if we did the arithmetic, we had a value of 8. That's about a 6% difference within our system. Or, yeah, about 6%. So slightly less diffusivity and slightly less under prediction. So those are 2 really important things to consider. Now, as I mentioned before, slide 26, as we talked previously, is when we had temperature dependence. And we're going to do that both in the finite volume and finite difference method to compare. But that is just for reference. If you guys jump back in your lecture, you'll see where we've mentioned that. Now, you will see on your first homework how to use these 2 types of averaging techniques. And what you're actually going to see is you're going to get pretty reasonable results by using both. A way to overcome this is we just kind of, put more control volumes, more cells within our model. You also get to play around with the insulating boundary condition. So that rounds out everything we needed to cover from lecture 2 about our one-dimensional steady state diffusion equation. Do you guys have any questions before we take a break and jump into lecture 3 where we discuss non-uniform grids? No? Okay. Well, let's do this. Let's take a quick 5-minute break, and then we'll come back, jump right into lecture 3. Now, let us jump right in. So today we're going to talk about, and once again, I had a small brain fart. Finite difference, that is my first love, because everyone learns finite difference before finite volume. But we're going to formulate the finite volume diffusion equation for non-uniform grids, because oftentimes we can't make a uniform grid. It's just incredibly hard. Oftentimes you don't want a uniform grid, especially when we start talking about flow problems, because you want a high density mesh in regions where you're going to expect your boundary layer to form, depart from the surface, eddies and vortices to form. But in your free stream, you really don't care about much. So you guys probably seen a lot of situations where we don't have uniform grids. And we're going to talk about how to implement that. And then, since we don't quite have access to CRC facilities right yet, we're not going to be able to jump into the tutorial, the hands-on portion of how we can generate meshes for different solvers. We will do that, and we're going to take these meshes into different solvers. We're going to learn how to set up the solvers, run them, then compare them to our own in-house codes. I did include a link to some videos, but unfortunately, we're not going to be able to jump on and do that today. So let's get started. Now, let's recall our general transport equation, where we had the time rate of change of our conserved quantity within our control volume, i.e. del by del T of rho phi. And this represented the accumulation of our conserved quantity phi within our control volume. Then we had advection, and recall advection was due to the motion of particles within our system. There had to be some velocity associated with this. And this is where we had the divergence of the quantity rho v phi. Now, in a situation where we have no fluid, i.e. we have no movement, v is equal to 0, and our advection drops out. Now, we spent last week and a little bit of today talking about diffusion, where we had the divergence of gamma grad phi. And we tack on a generation term, because we can generate some of our conserved quantity within our system. So far, we're working with just this portion of the equation. Next week, we're going to incorporate this guy and hopefully this guy. Then we'll get into advection, flow problems. Now, recall, phi is our conserved quantity. Typically, this is energy in the form of enthalpy or mass or species. Gamma is our diffusion coefficient. As we saw for all our diffusion problems, gamma was equal to our thermal conductivity. And rho is our density. Now, we're still going to focus on our diffusion term. We're not going to branch out. And we know how to do this. We set that up last week. So we're going to recall for our 1D diffusion equation, cast a finite volume formulation, AP phi p, that is, as we're solving for our conserved quantity phi at our cell center P, we have to know that of our neighbors, A west and A east, and our leading coefficients, where A west was our interfacial area between our west cell and our centered cell times the diffusivity at this interface. And we just learned that we can either do an arithmetic average or a harmonic average per the quantity delta xw. And delta xw is the space between our cell centers, W and P. AE has the same formulation. A east is our area of the interface between these two cells. It has a diffusivity, gamma east, and delta x east is the distance between our cell centers of P and E, those two volumes. So let's populate those guys. And AP is just the sum of A west and A east. Now, what's really awesome about this is we can take this equation right here and directly apply it to a non-uniform grid situation. A non-uniform grid is going to be where delta x west, and delta x east aren't constant as we move along our domain. And we see this all the time. Now, let's look at an example, because the best way to show really how awesome this method is just to jump right in. Now we're going to reconsider example 1 from our previous lecture. We're going to keep the values for the length of our system, which was equal to unity, our diffusivity, which was equal to unity, in our previous problem, our temperatures. So phi naught we kept as 100, and phi L we kept as 200 degrees, I think centigrade, and A east and A west. We set those equal to A and gave it just a value of unity. But now delta x is going to be a linear function of length. So we have delta x, and this is equal to the length of our domain, which is equal to unity, times x per n. And n in this situation, we're going to have 10 control volumes, plus L divided by 2n. So we can see in this particular situation, as we progress along the length of our domain, our dx is going to change. Delta x1, this is going to have a value of L per 2n. So we have 1 divided by 2 times 10 is 20. And then you can see as we progress what values we're going to achieve. Now, we want to be able to solve this type of problem and compare it to the same solution where we had a uniform grid. So what we have to recognize now is in our previous code that we used last week, we set delta x to a constant. Now, delta x here in our code, we're just going to set as a vector because there's going to be 10 unique values because we have 10 control volumes. Additionally, delta x west and delta x east are going to be variable. And that's not too much of a problem. So let's see this in application. Now let's start with our first control volume, and we're going to set this up in a very generic manner. Let's look at CV1. And as opposed to starting with the interior, we're just going to move sequentially through our domain. So if we're looking at CV1, here is our center cell P. So our diffusion equation for this would be AP times T1, where T1 is the center, or the value of our cell center, P, minus A east T2. This is our eastern cell, and T2 is that temperature, minus A west T naught. Now, we'd recognize, and I didn't do the modification to our boundary, that this is actually a boundary, T boundary, because there is no western cell hanging out here, because we are at the end of our domain. But for coding simplicity, I just left this as A west T naught. Now recall, for this, we're going to have to use half our distance. Now, to do that, and I want to make sure I didn't have a typo, which I think I do at the moment, we have to modify delta x west. And our first one, our subscript is going to indicate where our stencil is placed to be 1/2 of delta x1. So A west would, our leading coefficient, considering our first control volume, would be A west, the area of our interface right here at our boundary, times the diffusivity, gamma west, per, and let me write it this way, because I did miscopy this over. Delta x1, where delta x1 is the width of our first cell. And we want to divide this by 2, because our cell center is at the center, i.e. delta x w1 would be the distance from our left-hand boundary where we have our Dirichlet boundary condition to our cell center. And this would simply be equal to A times 2 lambda west per delta x west 1. So we have the factor of 2 taken into account because we are at the boundary. Now our coefficient A east is simply our area A, and we're going to assume our areas are constant, times our diffusivity at this eastern interface, lambda east, which we are treating as constant, per delta x east 1, where delta x east 1 is now the distance from our cell center, P to E. And we see delta x east 1 is obviously greater than delta x west 1, and they are not equal or differ by a factor of 2. That is, we can't just call this, 2 times delta x west 1. They're not, because we have a non-uniform grid. So what we're going to do is generally set up this equation. And I will make the modifications to these slides and push the most recent version to Canvas just to correct that little typo. Now, the reason why I'm doing this is we're going to see this kind of evident in our code, and we'll bring up the MATLAB ever so shortly. Now let's move to control volume 2. We're going to shift our stencil downstream. So what we do is we write our diffusion equation, AP, and within parentheses, recall that 2 is indicating that we are operating on our second control volume times T2 minus A east T3. T3 is our temperature at our third control volume's center minus A west T1. And now we actually have a western cell. And this is equal to 0. Now, all we have to do is be cognizant of our change of our delta x west and delta x east variables. They are going to have unique numbers. So A west 2 would be the coefficient between our west and P cell centers. And this is going to be equal to the area of our interface times our diffusivity, which is lambda west, per delta x west 2. And delta x west 2 is a value between our western and our centered control volumes. A east, this just becomes our area between our two control volumes times our diffusivity per delta x east 2. Notice how all we did was specifically to note with respect to what control volume we are operating on. Our stencil and the formulation of our 1D diffusion equation remains unchanged. We're just repeating it, right? This looks identical to what we did last week. And that's why the finite volume method is really powerful. It's really robust. We don't have to do any drastic changes. We begin to see the pattern, right? For our third control volume, we could say APT3 minus A East T4 minus A West T2 is equal to 0. And we can define our coefficients. A West 3 is equal to A lambda W per delta X West 3. A East 3 is equal to A lambda E per delta X East 3. And it's very formulaic. We can proceed all the way down through our interior control volumes. AP T4 minus A East T5 minus A West T3 allows us to populate our equation for our fourth control volume. We can find A West 4 as our area of the interface times the diffusivity at that interface times delta X West 4. And this gets incredibly formulaic. Now, the last thing we'd have to do is look at our 10th control volume. Now, our 10th control volume is going to be the largest because our grid sizing is increasing as we move along the length of our domain. Now, our diffusion equation, since we are focusing on our 10th control volume, is we're going to take AP T10, where T10 is our conserved quantity at the center of the cell. In this situation, it is temperature, minus A east T11. Now, there is no A east T11. This is AB TB. But what we do know is T11 is going to be our second Dirichlet boundary condition, where we have a temperature of 200. And we know how to modify A east. And once again, I copied that over wrong, so I will definitely fix that and push it for you guys. But before we get into that coefficient, we have minus A west T9. And I'm going to represent that really compact dark gray cell as that. That was just to show, ellipses, because I couldn't fit all 10 on here. That's going to be our leftmost cell. So once again, it's the same formulation. Now, A west evaluated with respect to our 10th control volume, AW10, is simply our area between these two cells, where which keeping constant is 1, times our diffusivity is 1 per delta x west 10. Delta x west 10 is the difference between our two cell centers of our W and P cells. Now, A east 10, well, this guy is simply equal to A east, the area of our interface, times our diffusivity, lambda east, per delta x 10, which is the length of our cell divided by 2. And that gives us delta x east 10. So we can call that guy A 2 lambda e delta x east 10. So really, it's identical to the code we've constructed thus far for a uniform grid. I don't see any major changes thus far, just besides us defining these variables separate. And I'll show you how we do that. Now, though we have our equations, we're just going to put this in matrix form. Recall for our control volume 1, we had AP T1 minus A east T2 minus A west T0 is equal to 0. Now, A west T0, since T0 is a constant, this moves to our right-hand side in our B matrix. For our second control volume, we had AP T2 minus A west T1 minus A east T3 is equal to 0. So we populate our A and B matrices the same. And we move all the way down. Now, let me pull this guy up, and I'd suggest you guys do the same. So we have a script called lecture 3, example 1.m. And what we're going to do is going to walk you through of how we set this up. And I'm going to spend this time to first go over our script from lecture 2. And then show you how we modify for a non-uniform grid. So I have to approve myself to share my own screen. And let me update the size of the text. This will hopefully work momentarily. Preferences, fonts, 20. Beautiful. Okay, if I stop the share, And then I begin to share. Hopefully that comes through okay. Now let's take a look. So up top, we really have lecture 2's code where we have a constant dx. Now I've annotated this in somewhat of a sensical manner as we progress through the problem. Now let's first look at if we have a constant dx. So let's define our constants within our system. We said the length of our domain was 1 meter. And I'm going to specify the diffusivity of our east and west cells are both equal to unity, as well as the area of our interfaces between our east and west cells in relation to our cell center P as unity. Now, in this problem, we wanted 10 control volumes, which I'll use as capital N. Now, lowercase n is going to represent the number of nodes. So if we have 10 control volumes, that means we have 12 nodes because we have node 0 and node 11. These reflect our two boundary conditions. In a situation where we have a constant dx, our delta x west and delta x east are the same as dx, the width of our control volume, which is simply L divided by N. So that defines our domain. Now, what I did here is amended lecture 2's code so we can define our nodal points. And this is where our temperatures are being solved. And I use these nodal points for dx of a constant value for us to easily plot and see what's going on. So nodes, I'm going to specify as a 1D array that has a length of lowercase n, i.e. there will be 12 values for our nodes because we have 12 nodes. Node 1, the first node in our domain, which we indicate as node 0 on our slides, is going to have a value of 0. Now note, MATLAB doesn't allow us to have a 0 indice like Fortran. So we just had to be very careful of this offset node. Now node 2 is going to be the first node. That's going to be the center of our first control volume. That's going to be dx per 2. Then for our interior nodes 3 to n, we just continually add a dx to each preceding node. And then we can define our two end nodes. Now, if you do a double % sign, it allows you to evaluate a particular section. So let's write out our nodes and look at them. Our first node is 0. That's the left-hand side of our boundary. Our second node is the node that represents the center of our first control volume, which is 0.05 meters. Now, in this situation, we have a value of dx of 0.1. So each of our interior nodes is increasing by amount of dx until we hit our last node of 0.95, where we add half a dx on to get to our 10th node. And I will pull up a picture that illustrates this. So if we imagine this was a uniform grid, delta x1, delta x2, delta x3, all the way up to delta x10 would be a value of 0.1. So our first node is 0, and then as we go to node 1, that's a difference or a distance of delta x per 2, or 0.05. And then we'd move a delta x, a delta x, a delta x, all the way up until the end. So these nodes just help us really identify, where our temperatures are being solved. Now we can define our variables of interest. In this problem, we are interested in solving temperature. So I'm going to define it as a 0 array. It's going to be a one-dimensional vector of, we could do lowercase n, 12 values. 10 of them we are solving. Those are our interior values. And 2 of them, temperature at 1 and temperature at the end of our array, are going to be our specified boundary conditions. Now, for us to make our coefficient matrix, we recognize that we have 10 equations and 10 unknowns. So I'm going to make it a 0 array, i.e. an array that's full of zeros, that's n by n, or a 10 by 10 array. And lastly, our right-hand side, our B matrix, I'm going to populate that as all zeros of an n by 1. Now, we can define our two boundary conditions, our two temperatures. On the left-hand side, we had a temperature of 100, and on the right-hand side, we had a temperature of 200. So T of 1, our first temperature entry, is going to be 100, and this corresponds to node 1. And T of n is 200 Kelvin. This corresponds to our last node, our 12th node. Now, all we have to do is define our coefficients. Now, I'm going to define our coefficients for the interior of our domain, not when we considered our first and last control volume. A west was simply equal to the area at the interface between our P and west cells times our diffusivity per delta x west. A east is equal to the area of our interface between our P and east control volumes times the diffusivity per delta x east. And AP is equal to A east plus A west. So what I'll do, and Josh last week shared a really cool code, a little MATLAB command that allows you to evaluate a tridiagonal array or populate a tridiagonal array very, very easily. So Josh, I don't know if you have that handy and you want to throw that back up in the chat, you are more than welcome to. I suggest you guys can use it. I'm old school. I just like loops. So what I did here was populate the coefficients for the array, and I'll come down here and show you. The diagonals of our array, not considering the first and last, because A east and A west are going to be ever so slightly different. So right now I have all the diagonals except the first and last populated in this loop. Now, for me to populate AP, i.e. the first diagonal and the last diagonal, I just have to make sure I consider the modification to A west and A east. And I did so here. So coF11 would be the first entry of our coefficient matrix. This is A east plus 2 times A west. Now I just did 2 times what we had initially existing, because we have our dx per 2. The last entry for our coefficient array, I did A west plus the modified A east, as we saw when we evaluated our 10th control volume. So we can come up here, look at our coefficient, and we see our first and last coefficients do differ from those of the interior. And this is a very good sanity check. If you had all 20s, something's going a little bit funny. Thanks, Josh. And you guys should be able to see that in the chat right now. And you guys can make a cool tridiagonal array. Now, all we have to do is populate our off diagonals. And what I have here is just, once again, 2 for loops and 2 conditions. For I is equal to 1 to n, for j is equal to 1 to n, if I plus 1 is equal to j, that means we are going to populate our upper diagonal, and we have a value of minus A east. If j plus 1 is equal to I, that means we are in our lower diagonal, and I will populate minus A west. In doing such, we can look now at our coefficient array. And see our upper and lower diagonals are all populated. And we expect A east and A west to be the same, of minus 10. Now all we have to do is populate the right-hand side matrix. Now recall our first equation. We had AP phi P minus AE phi P minus AW phi W is equal to 0. Now we have A east populated, but A west gets kicked on over to the right-hand side of our equation because it's multiplied by T naught, i.e. our Dirichlet boundary condition, 100 Kelvin. So T1, recall, we defined up here as the temperature the first entry of our zeros array, which had 12 entries, and T1 was the first entry, i.e. our boundary condition. So we multiply T1 through. Now recall when we looked at control volume 10, we had AP VP minus AE VE minus AW VW is equal to 0. We did have a cell to the left, i.e. A West was existent, but now A East gets kicked to the right-hand side equation, and we have to multiply that by our ending temperature, T end, our second three-way boundary condition. In doing such, we have our B matrix defined. We have our two entries reflecting our two equations for our control volumes. This is awesome. Now, all we have to do is recall in matrix form, we have our coefficients, we have our temperatures, we have our right-hand side. So X is equal to A inverse B. So we just take our coefficient matrix and use our backslash B, because MATLAB tells us that's faster than calling inverse A times B. And that's going to give us our temperatures for control volumes 1 through 10. Now note that if we're interested in looking at the temperatures of our boundaries, I'd have to bring in my two boundary conditions, T1 and Tn. So all I did here was define a new variable, temperatures, and temperatures is going to be a 1/12 vector. And using horscat, which means horizontally concatenate, I can stitch on T1 and Tn to the interior temperatures we just solved for. So right now I have an output statement just telling us our temperatures, the locations, and a plot. So let's take a look at this code. So right now, we have our, right down here, when X is equal to 0, we have a temperature of 100 Kelvin. This was our left-hand side boundary condition. Up here, when X is equal to 1, we have our right-hand side boundary condition, 200 Kelvin. Now, each of these dots is representing a cell center. Now, what's really cool is if we look at this guy, and let's bring him right about there. That's kind of ugly, but it's okay. This is representing our first control volume. That is node 2, which is representing, i.e. node 1 in our written schematic, i.e. the first control volume. And you can see, if we trace these up just a little farther, you can kind of see how our control volumes are forming. Now, of course, our control volumes are occurring on a diagonal because that's how our temperature plot is going to evolve. This is our second control volume. And you see they all have the same dx of 0.1. We could continue down, and this is slightly cathartic. And I don't quite know why, of just drawing out what would represent our various control volumes as we move through. So that's pretty neat. So this is really just the code we developed last week to solve our system of equations. Now, I'd really suggest you guys take a look at that, make sure you understand everything that's going on, play around with it a little bit. Because you guys are going to have a pretty fun homework that just has modified boundary conditions and modified areas. Now, the modified areas, that's not going to be too much of an issue. For what we're going to talk about today is, a non-uniform grid, and you can apply the same logic, same routine to a modified area. Now, starting down near line 100, this is where we're going to evaluate our variable dx, i.e. our non-uniform grid. So what I did is I cleared our variables. Clear vars is a very useful command. I clear delta x west, delta x east, a west, a east, AP, our coefficient matrix or B matrix, our temperatures, our temperature solutions, and what we have concatenated as our temperatures. I could also clear dx. Now, we're going to take a very, very similar approach. And I apologize for doing this online. This would be so much better if we were in 318 Benedum. You all had a computer in front of you, and we could work through this. But you have the video, you have the script, so you can always come back and consult if something isn't sitting quite right. Now, let's look at our variable dx. First, I'm going to define the number of nodes. We have 12 nodes because we have 10 control volumes, and then we have 2 nodes on the left and right-hand side in totality. So we know we have 12 nodes, just like the previous problem. And I want to define our nodal points, where they exist. Where are our cell centers? So I'm going to take an expression, dx, and I'm going to make it a function of I, the number of control volumes we have. So x is going to signify our physical space. It's going to be a length space from 0 to 1. And if we want this in very robust, we can go from 0 to L by n number of control volumes. I'm going to take the equation that was provided within our lecture notes. dx of I is equal to L per n times x of I plus L per 2n. And notice how dx, now as opposed to being a constant scalar value, is a vector. When we run this, what we're going to see is as follows. dx is actually specifying the length of each of our control volumes. Our first control volume is going to have a length of 0.05. Our second control volume is going to have a length of 0.0611. Our third control volume is going to have a length of 0.0722. And you can see how these lengths, our dx's, are increasing. This is going to be 0.0833, 0.0944, 0.01056, 0.1167, 0.1287, and this is 0.150. So our last control volume, our 10th control volume, is actually 3 times longer than our first control volume. And we can see this in this picture. This 10th control volume is actually 3 times longer than this control volume. So delta x1 has a length of 0.05 meters. Delta x2 has a length of 0.0611 meters. I actually drew this to scale. Delta x3 has a length of 0.0722 meters. Or sorry, meters. All the way through. So we have a non-uniform grid spacing. And what I did here is a continuity check. So if we sum up all our delta x's, it should be equal to unity. Now, we talked about this before, computers, they store numbers pretty well. But if you said, if sum of dx does not equal 1, throw an error. Well, machine precision is getting down 1 e minus 15, 1 e minus 16. So I said the sum of dx, i.e. we take the sum of all the lengths of our control volumes less 1. This should be 0. And if it's greater than 10 to the minus 15th, then we have an error. Just because now it's hard to think about absolutes in a computer. So if I run this, no errors are thrown. That is, if we take this value, sum dx, it is indeed equal to 1, at least the way it's formatted. So the first thing we have to do if we have a non-uniform grid is definitely specify the lengths of each of our dx. You could do it manually, but I like doing a code, make it really robust for if I want to change the number of control volumes. Say I set this to 5. It works down here, no domain discretization error. Say we want 100 control volumes. No domain discretization error. It is robust. Now that we have dx, i.e. delta x1, delta x2, delta x3, I want to know my nodal locations. And the reason why I want to know my nodal locations is as follows. We're going to have to calculate delta x west 1 and delta x east 1. We're going to have to calculate delta x west 2 and delta x east 2. We're going to have to calculate delta x west 10, delta x east 10. And the easiest way for us to do that is if we have our nodes, all we have to do is subtract them. For instance, if we know delta x1, all right, our cell center is going to be delta x1 divided by 2. So I'm going to take that value of node 1 less the value of node 0, and that specifies delta x1. So what I did is just took the script from above and defined our nodes. Our first node is 0. Our second node is delta x1 divided by 2. If we look at our picture, delta x1 divided by 2 is going to give us this node right here where we have a 1. Now, please note, as mentioned, MATLAB can't have a 0 index. So we start at 1. And this is just, something that might cause confusion when you're doing the coding. You just have to be very careful of your indices. Now, for the remainder, 3 to n, the remaining nodes are nodes I minus 1 plus dxi minus 2 plus dxi minus 1 divided by 2, the average of those. And if we do this, we can look at our nodes. And we can pull this up and make sure it makes sense. Our first node is when x is equal to 0. Our second node is half of delta x1, which is 0.025. Now our third node, which we didn't know as our second control volume here, and our second node, we could take delta x1 plus delta x2 divided by 2 and add that on. There's a large number of ways you can find your nodes. I just did it as such and took the previous node, did the average of those two. It works out quite nicely. So we have our nodes defined. Now, all we have to do is define our nodal spacing, i.e. delta x west and delta x east. That's it. We're almost to the end. So when we do this, we need to determine delta x1 west and delta x1 east. So delta x west 1. When we're at our first node, all we have to do is take node I plus 1 minus node I. So this would be 2 minus 1. That's our distance. Delta x east would be I plus 2 minus I plus 1. And between these two control volumes. Repeat as we move down the line. So we have all our delta x's defined. And you guys can play around and look at these numbers, double check, work it out by hand. It looks kind of nice. So if we look at this guy, the only thing we changed is we created dx as a function of space. We defined our nodes as a function of dx. That is, our nodes are going to vary as a function of our position as we move down the length of this domain. And delta x west and delta x east all change. Now, what's really nice about this is we can look at some of these variables. Delta x west. And you can go through and double check. Our first spacing, delta x west 1, and that should obviously be 0.025 because that's delta x divided by 2. Now delta x east, this would be this node less that node. And that's going to give us the value of about 0.0556. So you can go through and double check by hand. I did so earlier today, did all the math in MATLAB, did it all by hand. It all checks out. Now, besides that, everything about our finite volume method is one and the same. We'll once again reinitialize our temperatures. You can do n plus 2, or n, the number of nodes, as opposed to number of control volumes plus 2. We'll define our coefficient matrix, pre-populated with zeros, and we'll define our B matrix, pre-populated with zeros. I will redefine my boundary conditions, and all we have to do is define our coefficients. Now, what's really nice about this is since we already had delta x and then delta x east and delta x west defined as a function of length, when we define our coefficients a east, a west, and AP, we can just call in delta x east, delta x west, and then what we solve for. We don't have to necessarily do that special 1/2 and populate that at the end because this is already pre-computed. So we have to make sure though that these are a function of our space, i.e. which control volume they're being evaluated at. So we do a simple summation. Now we'll just populate our coefficient matrix all in one go. So we'll do a double for loop. If I is equal to j, we populate AP. If I plus 1 is equal to j, we populate a east, the negative thereof. And if j plus 1 is equal to I, we populate a west, the negative thereof. Now, I want to show you something really cool. If we look at our coefficient matrix, it's going to look drastically different, right? Our values for AP, if we look at the interior, none of them are the same. If we look at A east, none of her values are the same. If we look at A west, also none of her values are the same. That's because we have this variable delta x east and delta x west. So that's okay. We just always want to make sure our off diagonals are negative. Our diagonal right down the center is positive. And then all we have to do is, once we feel confident with our coefficient array, is we can populate our right-hand side matrix, or B matrix. B1 would just be A west 1 times T1, and B end would be A east end times T end. Now all we have to do is solve it. Matrix inversion. Temperature is equal to inverse of our coefficient matrix times our B matrix. And once again, temp is going to give us our interior temperatures for our 10 interior control volumes, which we kind of tack on our two boundary conditions to the end. And what we're going to do is click the run button. And we're going to take a look at this. Now, the first part of the code where we had a constant dx. Let me do this. We have a constant dx. We've already looked at the solution, and we know it makes sense because we definitely have a linear temperature profile, but we saw these circles right here are representing the cell centers of our 10 control volumes. And you can see they are equally spaced. Now, as we solve for our non-uniformly spaced code, and if you have this running, you're going to see that first cell center is at 0.025. It's nice and close. And then we get a little farther apart, and we can see they increase in space as we move farther down the length. Now, the original solution, we plotted that with a black line, and our new solution, we're going to plot this with a blue line. And we can see here, now they overlay quite nicely with one another. If we zoom in on any particular region, these lines are over top one another. We're getting, minor variation. Oops, I went too far. Incredibly close, right? Near imperceptible. And in your homework, what you're going to be able to do is quantify the L2 norm of your solutions and see how they deviate. But right, these guys are pretty close to one another. If we look at these number lines down here, we got 0.49103, 0.49103, and this is 255, this is 256. So you're talking maybe a fluctuation and like 8th, 9th, 10th decimal place, which isn't much. If we wanted to throw in more control volumes, and we could look at our solution, things would probably line up a lot nicer. With 100 control volumes, you can then go in and check. So what's incredibly nice and robust about this algorithm is it's really easily extended to more complicated scenarios. So if any of you guys have done work with numerics in any fashion, any open source CFD software, any commercial CFD software, finite element, you know that creating a uniform mesh is almost near impossible for most of the systems you're looking at. Because in real life, you're never going to be able to have uniform mesh density. You're never going to have uniform mesh spacing. There's always going to be curvature. There's always going to be weird things going on with your model. And for us to, extend this in the finite volume method by simply just predefining our nodal locations and our delta x east and delta x west variables, it runs very, very smoothly. Our solution algorithm doesn't change. Now, I want to illustrate why that is of importance. So for you guys who've taken numerical methods, ME 2060, most of the time when you guys did the finite difference method, you used a uniform grid spacing because it made the formulation or evaluation of your derivatives quite easy. Now, if you have a non-uniform grid, you have to use Lagrange polynomials. So if we look at our 2-point central difference equation for the first derivative, and I'm going to bust out my numerical methods book here because I forget. 2-point central difference. I'm going to write this down. So for a uniform grid, our 2-point central difference, f prime of x of I is equal to f of, I can write this a little nicer, f of x of I plus 1 minus f of x of I minus 1 per 2 delta x. So for a uniform grid, our 2-point central difference is really easy. If this is I plus 1, this is I minus 1, we just grab this point, we grab this point, and we average them because they are spaced at delta x. Now here's the Lagrange polynomial for our 2-point central difference for the first derivative. It's messy, right? We have really 3 terms populating this equation, and within each of these we have a pretty substantial denominator. And the numerators aren't too pleasant either. So what I'm saying is it can easily be done within the finite difference method. You just have, probably a comparable amount of coding that needs to be done to handle a non-uniform grid. Now, if I look at this, I don't know if it's stated what the order of error is, at least for your 2-point central difference method. Your error is on the order of delta x squared. For a uniform grid, here, I don't know offhand. I don't know if it is second order accurate. It may be. May not. But with the finite volume method, we're really only getting first order accurate solutions for non-uniform grids. So there may be trade-offs. In situations for diffusion problems, the finite difference method might be able to give you, less error, i.e. your error is on the order of, say, delta x squared, delta x cubed, delta x to the fourth, which is going to be incredibly small in comparison to the finite volume method. But it comes at a cost of your Lagrange polynomials. So there are trade-offs. It all depends upon the situation that you encounter and what error you're trying to, say, minimize. So I'm not saying the finite volume method is, a silver bullet, but as we saw in that MATLAB example, it's relatively easily adaptable for non-uniform grids. We didn't have to change the formulation of our derivatives in any way, shape, or form. We just, defined our nodes and our delta x east and delta x west values based upon those non-uniformly spaced nodes. So I know that example was a little bit quick, but hopefully walking you through it and letting you guys actually have that code, play with the code, and see how things are cast and compare it to the notes will be incredibly useful, as opposed to me just saying, here's the theory and go code this up. You guys will be fine. So before we progress just into a final conclusion of our content, does anyone have any questions related with, the non-uniform grid? How things are set up, considerations that need to be made?
Is there a reason why we can't just have uniform grids?
Yeah. I wish I could pull up these pictures, but yeah, definitely. For instance, our lab group just does a lot of the numerical modeling for thermoelectric generators to verify JPL's analytic codes. So sometimes they give us geometries, and you have a three-dimensional volume. You will have an element that's length, width, and height. It is rectangular because that's really simple to make. But you would think of in a situation where, say, your length L, width W, and height H, if you try to get a uniform grid spacing based upon the physical dimensions of that geometry, you might now be getting mesh on the order of like a micron. So as opposed to picking a reasonable mesh size, which might not, say, be uniformly spaced in delta x, y, and z directions.
So with like enough computational power, we don't really need, like in the perfect world where we have all of the computational power we want, we don't really need non-uniform meshes.
Correct. Yeah. If, say, we had, infinite memory and quantum computing, we could. But let's do a really basic example. Let's call this like 5.3. Let's call this 4.1. And let's call this like 11.2, right? And say we wanted to make a uniform differential volume where you need, delta y, delta x, delta z to be all the same value. So really, what's the least common denominator here? Well, we could say, 0.1. So we could call that 0.1 centimeters. That'd be a really, relatively easy value to hit, but 0.1 centimeters might be too large of a mesh resolution because certain problems, as we mentioned within the finite volume method, at most you're going to be second order accurate. This is 1,000 microns. Okay. Now, oftentimes, when you guys are doing certain types of modeling, certain types of physics, you're definitely going to go through a grid-independent study. So you're going to refine and refine and refine your mesh, and you're going to track the evolution of your solution, and hopefully it converges to a value. Now, for instance, in our modeling of these devices, we try and hit 40 microns for our, max size. So in this situation, we could cut it down to 100, which is just too big. we actually have energy imbalances that just aren't acceptable to us. Or we could cut it down to 10 microns. And you go, okay, if I have 4 of these guys in a junction, and then there's 2, well, actually 4 of these per couple, and there's 2 of them in a junction with the interconnector. Suddenly, if you're building something with a 10 micron mesh, this guy would be 41,000 micron. I'm just doing some math off the top of my head. What's 41,000 divided by 10? That's 4,100. And then 5.3. And I'll illustrate in just a moment why this is. And that's times 5,300. Then 11.2. And that'd be 11,200. So if I take 4100 times 5300 times 11200, if we did a 10 micron mesh just for this one thing that has these really, really tiny dimensions, you're talking about, I'm taking this to Wolfram Alpha because that's way too many numbers for me to count off the top of my head. That is 2.4 times 10 to the 11th, 250 billion elements. So sometimes this gets out of scale really, really quickly. Now, if this were millimeters, for instance, I'm going to cut out 3 orders of magnitude here. That's still 243 million elements. So if you're trying to always construct a uniform grid where you're solving for that one mesh size that allows you to have a perfect dx, dy, and dz, where it's uniform in all dimensions, that's a lot of elements. That's a lot of memory. And that's a tremendously long solve time. So sometimes you just can't get away with it. You're going to say, okay, we're going to have to at least limit whatever is acceptable within our model. We might have situations where we don't have a perfect differential volume. So yeah, I'd agree with you. If we had unlimited memory and fantastic computing power, cool, let's make it uniform. It's just currently not achievable. Unless you're in a lab that's really flushed with cash.
Are you just gonna walk into a Rivian wind tunnel?
Yeah, it'd be nice to. Pitt has some awesome resources. You guys are tremendously fortunate. Pitt supercomputer through CRC is actually really good. But yeah, we would need Los Alamos National Lab level supercomputing right here. So, yeah, oftentimes we just can't make a uniform one. You're going to have some variation. Now, it might be uniformly spaced throughout your domain, but as we're going to see in our 2D solver and 3D solver of our finite volume formulation, even if we have different aspect ratios, we have to take that into account. So you are going to have to, populate your delta x east, delta x west, delta x north, delta x south, delta x east forward, delta x backward, and populate those as different values, which then update your coefficients that then get taken into account when you solve your matrix. Another thing that I would mention, though, is sometimes you do want high mesh resolution in areas where things are happening. For instance, fluid flow. So you got a surface and you got a boundary layer forming, and it breaks up. So typically what you do is you do a kind of like a power law. So you can pack in a huge bunch of mesh right in this boundary layer, because that's where you want to capture all the physics. That's where you're determining your drag. And then once you get into your free stream, you can start expanding it out quite a bit. So in even fluid problems, having a non-uniform mesh is tremendously important, because you need a really tight mesh in areas that you want to, I always say capture physics, and people typically take that the wrong way, but where you want to resolve your system of equations and actually determine what's happening. And then in regions where you know it's free stream and it doesn't have too much of an effect, you make that mesh coarse so you don't have too much computation time associated with it. So that's kind of like a long-winded answer. Is that decent enough?
Yeah, thank you.
Yeah, you guys will see this. You guys are going to be playing on the supercomputing resources. You guys are going to be building models and running them. And what's great is I guarantee sometimes you're building some mesh and you think, I think that's enough elements. And then the system crashes because it exceeds the memory. And you go, wait, I thought this had 256 gigs. And it's like, yeah, that wasn't enough. And you're like, okay, I should make it a little coarser. I should lighten it up in some regions. Okay, so that's how we handle non-uniform grids. And in the finite volume method, that MATLAB code looked bad. Sit down, spend half an hour with it. It's actually not horrible. What I'd recommend, and I did this today, I drew out that system by hand. I did all the calculations for the nodes and DXs would be, and then compared it. Go, okay, this is how we could populate it using some for loops to get those nodal locations, delta x east, delta x west. You guys might have a more elegant expression. Cool, modify the code and use it. And then just see how, as you play around with the number of control volumes and things of that nature, or even the expression to show how number of control volumes is changing. Say you don't want a linear increase of delta x. Maybe you want a power law or exponential. Plug that in. See how things turn out. It looks a little scary at first. It's much easier than using Lagrange polynomials in the finite difference scheme. Okay, so last but not least is, we kind of talked about the non-uniform grid in a manner where we were defining nodes or cell centers. Now, what we really did is we generated our own mesh in MATLAB. And a mesh is really generating the grid or domain where our equations are being solved, where we're casting our ODEs or PDEs in a finite volume form motion and solving on them. And what we're going to do probably next week is we're going to jump into ANSYS ISEM to do some meshing. Now, there's a lot of softwares out there. You have your commercial software such as Star CCM, I think, which was recently bought by Siemens. You have ANSYS, you have COMSOL, you have open source codes. OpenFOAM is a big solver and meshing utility, as well as Gmesh. We're just going to use ANSYS ISEM because it's my preferred meshing utility because you have explicit control over everything you do, and we have licensing to it. So hopefully by next week, I'll be sending an email out, maybe this week or next, that says you guys all have access to CRC and a few instructions of how to log on. Really, what you're going to have to do is log on to Pulse. Once you're on Pulse, you select a VPN you're going to connect to. It's SAM, which was the old supercomputer's name. And then you're just going to go into your web browser, type in a cool little address, and you're going to be able to log on to one of the Viz nodes. It's a GUI-based node on the supercomputer that allows you to use a software in a graphical user interface form, as well as transfer files to and from. And we'll cover the basics of meshing. So we're going to kind of repeat these problems in ANSYS Fluent and ANSYS CFX and compare the results they give us to the results we're generating. We're going to develop some non-uniform meshes and compare the two. And it's going to be actually quite a bit of fun. Meshing is just a great time all around. And it'll begin to get you guys some exposure to the supercomputing facilities. By the end of the course, you'll definitely be running models on there. You can even run MATLAB on the supercomputer if you don't want to run it locally. And we'll go through how to access it, how to transfer files, how to run jobs, how to monitor jobs, how to post-process results, all that fun stuff. But we can't do that tonight just because we don't have access just yet. So there are 2 tutorial videos I put up. If you currently do have access to CRC and are a member of the ANSYS licensing group, jump on YouTube, check out that stuff. But if not, we'll get that going next week, and we'll have some fun building a few meshes. So with that, we end a little bit early tonight. I'll stay around and answer any questions you guys may have. If not, go enjoy your Tuesday evening.